Let's do a magic trick. We'll need 3 paper cups. Pour some water into the first cup, then swap the positions of the 3 cups. Can you guess which cup has the water? Is it this cup? Or maybe this one? So it must be this one. Nope, it's gone. How did that happen? Well, there's a secret ingredient, superabsorbent polymer powder. A superabsorbent polymer is a polymer with an extraordinary ability to absorb water, often hundreds of times its own weight. When exposed to water, the carboxyl groups in the SAP structure ionize, creating negative charges. These negative charges attract water's positive ions and form hydrogen bonds with other water molecules. This process repeats, forming a dense network of hydrogen bonds, allowing SAP to efficiently absorb and retain water. Check out this empty plate. Let's see what happens when we bring a piece of paper near it. Wow, the paper caught on fire. Let's do it again and see if we can figure out why. Look at the burning paper. Can you spot the flame? It's actually the alcohol burning. Why is the alcohol flame so hard to see? Alcohol flames are difficult to see because they produce a blue flame that is almost invisible in daylight. This happens because alcohols burn cleanly with little soot, have lower flame temperatures. The light emitted by burning alcohols is primarily in the blue and ultraviolet spectrum, which is less visible to the human eye, especially in bright conditions. First, let's light a candle. Next, we'll inflate a balloon and bring it near the flame. You might expect a big pop, but nothing happens. That's because I've done a little trick. I added some water to the balloon before inflating it. Why water protects a balloon from a candle flame? When the balloon is filled with air, the heat from the candle flame quickly heats the rubber, causing it to weaken and burst. However, when there's water inside the balloon, the water absorbs the heat from the flame instead of the rubber. The heat from the flame is transferred to the water. The water acts as a heat shield, preventing the rubber from reaching its melting point. This is supercooled water, and it was the hardest experiment I've ever done. Unlike hot ice, this is water that freezes instantly when I pour. So how exactly do you do this experiment? Water can be cooled below its freezing point without turning into ice. It's normally from 0 degrees Celsius or 32 degrees Fahrenheit. This is called supercooling because the water, without any impurities or disturbances, water molecules can remain in a liquid state even below 0 degrees Celsius. Actually, they are essentially waiting to begin freezing. When I put this frozen strawberry into supercooled water, it will trigger the freezing process. This disturbance causes ice crystals to form rapidly. The water will freeze almost instantly, forming ice crystals throughout the water. To do this experiment, you need purified or distilled water and a freezer. Place the water bottles in the freezer for about 2 to 3 hours. The exact time depends on your freezer's temperature, but you need to check the water bottles many times before the water turns into ice. Carefully move the supercooled water from the freezer. Once the water is supercooled, a slight disturbance can trigger the freezing process. You can try this experiment at home now and let me know how it turns out. Let's try a fun experiment. Take a piece of toilet paper and a glass. Put the paper in the glass, turn it upside down, and submerge it in water. Watch this. The water doesn't go inside the glass and the paper remains dry. Why is that? When you turn the glass upside down and submerge it, the air inside the glass can't escape because the water is pushing up from below. The trapped air creates pressure that prevents the water from entering the glass. As long as the glass remains upright and doesn't tilt, the air acts as a barrier, keeping the toilet paper dry. However, if you tip the glass even slightly, the air trapped in the glass will rush out in the form of bubbles. Water will then rush in and the toilet paper will get wet. Which one looks bigger? The A, right? Now let's move the A on top of the B. Wow, now the A looks smaller than the B? No, they're actually the same size. Pretty cool, huh? This experiment is similar. We have 2 sticks, one on the left and one on the right. You see the stick on the left is bigger than the one on the right, right? But actually, they're the same size. This plastic sheet is called a Leubor's lens or a lenticular lens. It's a sheet of plastic with a series of tiny cylindrical lenses etched into its surface. When light goes through it, These tiny cylindrical lenses bend the light around stuff behind it, making it look like the stuff isn't there. It's pretty cool. It's like a magic trick. For this experiment, we'll need a mirror and something called a 3D ambiguous cylinder illusion. You can download the 3D model from the internet and print it out using a 3D printer. It's really easy to do, and it'll totally blow your friends' minds. In this experiment, you need 4 small glasses of water. Then add food coloring. Place the 4 glasses next to each other and tie them together with a rubber band. After that, cut the stem of the rose like this and put it into the colored water and leave it overnight. Let's see what happens. Look, the petals change color. Isn't it magical? Roses, like all plants, need water to survive. When you place a white rose in colored water, it starts absorbing the liquid through its stem. Inside the stem, there are tiny tubes called xylem that carry water and nutrients upward to the flower. As the rose drinks the colored water, it's essentially plumbing the color right into its petals. Water evaporates from the petals, this process called transpiration. As this happens, the color from the water gets deposited into the petal cells, gradually replacing the natural white pigment. This process can be easily observed in a few days, and the longer the roses stay in the colored water, the more intense the color change will be. In this experiment, we'll be working with a balloon. Let's try hitting a balloon hard against a single nail. It pops easily. Now, let's try with many nails. Amazing, right? The balloon doesn't pop. Why is that? Imagine you're pushing a balloon with all your might against a single nail. Let's say 10 pounds of force. All that force concentrates on a tiny area, the tip of the nail. This intense pressure is strong enough to puncture the balloon's rubber and make it pop. Now, picture the balloon resting on many nails. The same 10 pounds of force you apply gets spread out among all the nails. Each nail only experiences a fraction of the total force, much less than the pressure from a single nail. This reduced pressure on each nail isn't enough to pierce the balloon, so it remains intact. It's like the difference between stepping on a thumbtack and lying on a bed of nails, where the body weight is distributed across many nails, preventing any single nail from applying enough pressure to puncture the skin. Look at that! The water freezes instantly. It's pretty cool, huh? Do you know what this is? This is called hot ice. It can instantly change from liquid to solid crystals. It is warm. It is not cold like ice, so that's why it is called hot ice. This experiment is very easy to do at home. You just need to go to a chemical store and buy sodium acetate trihydrate, which has the chemical formula on the screen. Next, let's pour it into a pot. Add a little water, heat it on the stove until it is completely dissolved, and then pour it into a glass. Let it cool to room temperature. Sodium acetate trihydrate can be heated to dissolve it in water. Once dissolved, the solution is allowed to cool down without being disturbed. This cooling process can allow the solution to remain in a liquid state even below its normal freezing point. This state is known as supercooled. The supercooled solution is highly unstable. When a disturbance occurs, such as shaking the container, adding a small crystal of sodium acetate, or touching the solution, it triggers the crystallization process. The molecules quickly arrange themselves into a solid crystal structure, releasing the energy stored during the supercooling process. The process of transitioning from a liquid to a solid releases latent heat. This exothermic reaction is what causes the hot sensation when the crystallization takes place. In this experiment, we need a tea bag. You empty a tea bag, stand it up, and put it on fire. It's flying. Why is that? The flying tea bag experiment shows how heat and convection work. When you fire it, the burning bag heats the air inside it. As the air heats up, it rises, creating a convection current. Once the tea bag burns down to a light ash, the rising hot air lifts the ash into the air, making it look like the tea bag is flying. In this experiment, we will need a jar, vinegar, and baking soda. Pour the vinegar into the jar, and then add a tablespoon of baking soda. Cover the jar with cardboard or paper to prevent the gas from escaping. Try tilting the jar toward the burning candles. What happens? Why do the candles go out? Baking soda and vinegar can extinguish candles because of the carbon dioxide gas produced when they react together. The carbon dioxide can displace the oxygen around the candle's flame so that the candles go out. To do this experiment, prepare a plastic bottle, a small plastic tube, some water, and dry ice. Make a hole in the bottle and insert the plastic tube. Pour water into the bottle, add dry ice to the bottle. Remember to wear gloves when handling dry ice. I forgot to wear them when doing this experiment. Dip the tube into the bubble solution. Wow, look at those bubble eggs. To keep the bubbles from popping quickly, add some glycerin to the solution and use a woolen cloth to cushion their fall. This is a fun experiment, right? Try this experiment to create impressive for your friends. We'll need 2 glasses and a candle that can be lit at both ends. Let's see what happens when we light one end, then the other. When you lit a candle at both ends, the flames create air currents and uneven heat distribution, causing the candle to burn unevenly and the flames to flicker. This makes the flames appear to dance. For this experiment, we need a piece of glass, toilet paper, and a lighter. Place the toilet paper on the tray, then add a bit of water to make the paper wet. Put a candle in the center of the paper and light it. Quickly cover the candle with a dry glass, ensuring it seals tightly with the wet paper. When the candle burns out, you can add more glasses or some heavy things and carefully lift the tray with the glasses like this. Why doesn't it fall down? As the candle burns, the air inside the glass heats up and expands. When all the oxygen is used up, the flame goes out and the air cools. It shrinks, creating a partial vacuum inside the glass. The atmospheric pressure outside the glass is higher, pushing down on the tray and holding it firmly, allowing you to lift the heavy objects. First, mix 3 spoons of baking soda with 2 spoons of sugar. Then, add lighter fluid into sand. After that, pour the baking soda and sugar mixture onto the sand. Light it up and watch the reaction. Look, what is this? When the mixture is ignited, the sugar starts to burn and releasing heat. This causes the baking soda to decompose into sodium carbonate, water vapor, and carbon dioxide gas. The carbon dioxide gas produced expands rapidly due to the heat. The expanding gas creates a foamy structure within the burning mixture. As the sugar continues to burn, it leaves behind a black carbon residue. The carbon dioxide gas inflates the carbon residue, forming a long black, looks like a black snake. It is very light and soft. In this experiment, we need a plastic bottle, alcohol, an air pump, and a tire valve. First, remove the bottle cap and create a small hole in it. Then, attach the tire valve to the cap tightly. Next, pour the alcohol into the bottle, put the cap back on, and shake well. After that, use the pump to inflate the bottle as much as possible. Quickly open the bottle cap. Boom! There's a cloud inside the bottle. Why does this happen? When the air pressure inside the bottle quickly decreases when the cap is removed or when the bottle is untwisted, the temperature drops inside the bottle as well. The pressure and temperature drop allow the water vapor inside the bottle to condense onto the rubbing alcohol particles, and it creates a cloud. As soon as you increase the air pressure, the cloud will vanish again just as quickly as it appeared. Before you do this experiment, you need to wear safety gear such as gloves and goggles. We need a drain cleaner, an empty aluminum can, and sandpaper. Use the sandpaper to scrub the outer coating of the can, then use a chopstick to suspend the can like this. Place the can in a container, then pour the drain cleaner into the container. Let's leave it in the drain cleaner solution for about 45 minutes. You'll notice bubbles forming around the can. This is hydrogen gas being released, which is highly flammable. Always perform this experiment in a well-ventilated area away from open flames. Take it out and see what happens. Wow, there is a plastic film inside the can. Drain cleaner typically contains a strong base, such as sodium hydroxide. When sodium hydroxide comes into contact with aluminum, can result in a chemical reaction that produces heat, hydrogen gas, and a dissolved aluminum compound, and there is a plastic lining becomes visible as the aluminum dissolves. Most aluminum cans have a thin plastic lining to prevent the beverage from reacting with the metal. Do you know what this is? This is not venom. This is ferrofluid. Ferrofluid is a liquid that becomes strongly magnetized in the presence of a magnetic field. It consists of nanoscale, ferromagnetic or ferrimagnetic particles, typically about 10 nanometers in diameter, suspended in a carrier fluid, such as water or oil. When a magnet is brought near the ferrofluid, the tiny particles align along the magnetic field lines, causing the fluid to form spikes and other interesting shapes. Ferrofluid is a magnetic liquid used in various applications. A small amount of ferrofluid can be used to create a liquid seal around the spinning shaft in a hard disk drive. The ferrofluid is attracted to the magnets surrounding the shaft, forming a barrier that prevents dust and debris from entering the sensitive interior of the drive. Some high-end loudspeakers use ferrofluid to cool voice coils. First, we add 3 spoonfuls of salt to a glass of water and stir until the salt is completely dissolved. This is a glass of salt water and a glass of fresh water. Next, place an egg into each glass. You will see that the egg in the fresh water sinks, while the egg in the salt water floats. Why does this happen? The reason an egg floats in salt water but sinks in fresh water all comes down to density. Density is a measure of how much mass is packed into a certain volume. Egg is denser than the fresh water. It displaces less water than its own weight. The water can't hold the egg up, so it sinks. When you put the egg in salt water, the salt water is now denser than the egg. The egg displaces enough salt water that weighs more than the egg itself. This buoyant force from the denser liquid allows the egg to float. You need a paper money. Place the money on top of 2 of the glasses like this, and place the other glass on the money. Now, let's try folding the money several times and repeat the steps as before. Look, the glass can now be placed on it, and even if we increase the weight. Why is that? A flat sheet of paper is inherently weak due to its thinness and lacks structural support. It easily buckles under pressure. Folding the paper increases its thickness, effectively creating multiple layers and its forming shapes such as triangles, and triangular shapes are particularly strong because they distribute forces evenly along their sides. Therefore, folding a sheet of paper increases its thickness, distributes the load more efficiently, and improves its overall structural integrity, allowing it to withstand a greater weight than a flat sheet of paper of the same size. In this experiment, we burned a piece of paper with a candle. It was easy to burn, right? Okay, let's do the next step. Wrap a piece of paper tightly around a glass bottle and hold it over a flame. Wow, the paper doesn't burn. What is that? Glass able to conduct heat. This means the bottle can rapidly transfer heat away from one point to another. When the paper wrapped around the glass bottle is exposed to a flame, the glass bottle quickly absorbs the heat from the paper. By efficiently conducting heat away, the glass bottle prevents the paper from reaching the ignition temperature required for combustion. So, the paper remains below its ignition point and does not burn. You can replace the glass bottle to a copper tube or aluminum tube. This is an easy experiment. You need a battery, a strong magnet like a neodymium magnet, and copper wire. The magnet is placed at the bottom of the battery, and the copper wire is shaped so that it touches both the top of the battery and the side of the magnet. When the copper wire touches both the battery and the magnet, an electric current flows through the wire. This current is due to the battery providing a voltage difference. When the electric current flows through the wire, it interacts with this magnetic field and generates a force called the Lorentz force. This force acts perpendicular to both the direction of the current and the magnetic field, so it pushes on the wire, causing it to spin around the battery and magnet. And this experiment is known as the homopolar motor. This is cold water, and this is hot water. Add food coloring to make it easier to see. Place a plastic sheet on top of cold water and carefully turn it upside down. Then place it on top of the glass of hot water. Now pull the plastic sheet slowly. You will see that the cold water quickly sinks and mixes with the hot water. On the other hand, place the hot water on top of the cold water. Slowly pull the plastic sheet again. Look, the hot water floats and does not mix with cold water. Why is that? When water is cooled, its molecules slow down and move closer together. This increased closeness results in a higher density for cold water than hot water, because it has a higher density, so it sinks in warmer water. As water is heated, its molecules gain kinetic energy, causing them to move faster and spread apart. This increased molecular spacing leads to a decrease in density for hot water compared to cold water. So, hot water, being less dense, floats on the surface of colder water. We're going to observe a magnetic field using iron filings. First, we'll wash the iron filings like this. Place a magnet under the bottle. This will help prevent iron filings from moving out. Add some water and shake the bottle gently. Now, bring the magnet closer. Watch how the iron filings align themselves along the magnetic field lines. Iron filings are weakly magnetic materials. When placed in a magnetic field, iron filings align themselves with the direction of the magnetic field lines. This creates visual patterns that allow us to observe and study the shape of the magnetic field. It's a simple experiment you can do at home. It looks pretty cool, right? In this experiment, we will know magnetic braking. You will need a neodymium magnet and a piece of string to hang the magnet. Try pulling and releasing the magnet. It will easily push the can away. Now, let's try placing 2 aluminum plates like this, and then repeat the steps of pulling and releasing the magnet. What do you see when the magnet moves over the aluminum? When a magnet moves over an aluminum surface, it creates a changing magnetic field in the aluminum. This changing field induces small circular currents called eddy currents. These eddy currents generate their own magnetic fields, which oppose the motion of the magnet. The opposing magnetic fields create a force that slows down the magnet's motion, acting like a brake. This process is used in various applications, such as in roller coasters and some braking systems, to provide smooth and contactless braking. In this experiment, we will use Coca-Cola and milk. You can change any other soft drink if you prefer. Pour milk into the Coke bottle, close the bottle cap, and shake 3 to 4 times, then place it on the table. Let's see what happens when we mix milk with Coca-Cola. Coca-Cola contains phosphoric acid, which reacts with the proteins in the milk. This reaction causes the proteins to denature and coagulate, forming clumps or curds. As the reaction progresses, the denser curds formed by the coagulated proteins sink to the bottom of the bottle, while the remaining liquid becomes clearer. The mixture initially looks dark, but over time, you will see a clear separation between the curdled milk at the bottom and a clearer liquid at the top. You might be surprised to learn that you can push a pencil through a water-filled plastic bag without the water spilling out in this experiment. You need water, a resealable plastic bag, and sharpened pencils. First, fill the plastic bag with water and seal it tightly. Push a sharpened pencil through the bag, how the water stays inside the bag. Wow, the water doesn't spill out. Why is that? Plastic bags are made of polymers, long chains of molecules linked together. These chains are flexible and can move around each other. When you push a sharp pencil through the bag, the polymer chains quickly rearrange themselves to surround the pencil. The chains form a tight seal around the pencil, preventing the water from escaping. What is this experiment? You will need a red cabbage, add some water into the blender, and add the cabbage. Blend it until it's smooth, then strain out the solids and keep the liquid. Pour the red cabbage liquid into different solutions, such as 7-Up, vinegar, baking soda, sugar, and water. Why do the liquids have different colors? Red cabbage juice changes color like litmus paper because it contains a pigment called anthocyanin. This pigment is sensitive to pH levels, which means it changes color when it comes into contact with acids or bases. Acidic solutions like lemon juice or vinegar will turn the purple cabbage juice red or pink. Neutral solutions like pure water will keep the juice purple. Basic alkaline solutions like baking soda or soap will turn the juice green or blue. First, pour some warm water into a glass, then add potassium phosphate crystals and stir until they are completely dissolved. You can buy this experiment kit on Amazon. Let's pour the liquid into the tree. Now, let's see what happens. Wow, is the tree blooming? Why does this happen? The solution travels up the cardboard tree through tiny pores, similar to how water moves through plant roots. This is due to capillary action. As the solution moves up the tree, the water begins to evaporate, especially from the edges of the cardboard. Evaporation is the process where liquid water turns into vapor, leaving behind dissolved substances. When the water evaporates, the dissolved salt is left behind. As more water evaporates, the concentration of salt increases until it reaches a point where it can no longer stay dissolved. At this point, the salt begins to form solid crystals. This process is known as crystallization. Therefore, this process will happen faster in a hot place instead of a cold room. First, we need to place a pot on the stove, then add water. Next, we put the eggs in and turn on the stove to boil. When the water boils, take the eggs out and turn off the stove. Now we have 2 eggs, one boiled and one not boiled. Here is the raw egg. Let's try to spin it and see what happens. We can't make it stand still. Next, here is the boiled egg. Let's try to spin it. It spins. Why is that? A hard-boiled egg has a solid interior, which means its center of gravity is fixed. When you spin it, the entire egg moves as one solid unit, allowing it to spin smoothly and steadily. On the other hand, a raw egg contains liquid inside. When you try to spin it, the liquid inside moves around independently of the shell. This shifting center of gravity causes the egg to wobble and makes it difficult to maintain a steady spin. Let's blow some soap bubbles. Now, rub a plastic PVC pipe with a cloth and see what happens when you bring it near the bubble. Look, why does the bubble move towards the pipe? When you rub a PVC pipe against a cloth, friction causes electrons to transfer from the cloth to the pipe. This gives the pipe a negative electric charge. A soap bubble is normally electrically neutral, meaning it has equal amounts of positive and negative charges. When the pipe is brought close to the soap bubble, the negatively charged pipe attracts the positively charged side of the soap bubble, causing the bubble to move towards the pipe. This is similar to rubbing a balloon on your hair, and it can also attract and move the soap bubbles. You need a battery 9-volt and steel wool for this experiment. Let steel wool come into contact with a battery. Wow, look at that. It's beautiful. Why does this happen? Steel wool is primarily made of iron, which is a good conductor of electricity. The strands of steel wool are very thin, providing a large surface area exposed to the air. When both terminals of the battery touch the steel wool, an electrical circuit is completed. Electrons flow rapidly from the battery through the steel wool. This flow of electrons generates heat. The thin strands of steel wool heat up quickly because they have a high resistance to the electrical current. As the steel wool heats up, it reaches a temperature high enough to ignite. The iron in the steel wool reacts with the oxygen in the air, creating iron oxide. This reaction releases more heat, causing a chain reaction that spreads through the steel wool. The reaction produces visible sparks and glowing areas as the iron burns. This is why you see the steel wool light up and burn when it touches the battery. Let's rub this teddy bear with a comb and see what happens when we bring it close to the water. Look, the water is bending. Why is that? When you rub a comb through a stuffed animal or your hair or a woolen cloth, you build up a static charge on the comb. This process leaves the comb with a negative charge. When you bring the negatively charged comb close to a water stream, the positive ends of the water molecules are attracted to the comb. This attraction is strong enough to pull the water stream towards the comb, causing it to bend. You need a lighter and a ballpoint pen for this experiment. First, remove the tip of the pen, then blow the ink from the pen tube to the tip of the lighter like this. Take it out and try lighting the lighter to see what happens. Wow, the flame is floating above the lighter. Why is that? The ink creates a thin film over the lighter's gas outlet, partially obstructing the gas flow and increasing the pressure as it escapes. This increased pressure pushes the flame slightly above the lighter's tip, making it appear as if it's floating. This experiment will show you how fluids with different densities can switch places. You need a glass of wine, a glass of water, and a thin plastic spacer, or a playing card. Place the plastic spacer on top of the glass of water. Carefully invert the glass of water and place it on top of the glass of wine. Slowly remove the spacer, allowing the fluids to come into contact. Due to the difference in density, the water, which is denser, will move down, and the wine, which is less dense, will move up, creating the illusion that the water has turned into wine. We need vinegar and salt. Pour the vinegar into the salt and stir until the salt is completely dissolved. Put the coin into the mixture and wait a little bit. You'll see the coin is shinier, right? Why is that? Over time, copper coins react with oxygen in the air to form a green or brown layer of copper oxide. This is what makes the coin look dull. Vinegar is an acid, and salt is sodium chloride, which provides chloride ions. When combined, they create a solution that effectively dissolves copper oxide. The acid in the vinegar reacts with the copper oxide, breaking it down. The chloride ions help to remove the dissolved copper oxide from the coin's surface. As the copper oxide is removed, the underlying shiny copper is revealed, giving the coin its restored luster. To do this experiment, you need a speaker that can connect to your phone, a rubber hose, tone-generating app, and your camera must be set at 24 FPS. Why does the water flow down like that? Sound waves are vibrations that travel through a medium, such as air or water. The frequency of a sound wave is measured in hertz, which indicates the number of vibrations per second. When you set a speaker to emit a 24-hertz sound wave, it vibrates 24 times per second. This vibration can be transferred to a stream of water flowing from a hose or pipe. If your camera is set at 24 frames per second, FPS, each frame of the video captures the water at the same point in its vibration cycle. This creates the illusion that the water is standing still or frozen, because each frame shows the water in the same position relative to the sound wave. This phenomenon is known as the stroboscopic effect. Let pour water into the dish. The water is blue because I mixed in a bit of food coloring. Place the candle on the dish, and then add a bit of alcohol to the bottle, shaking it well. After that, cover the candle with the bottle. Let's see what happens. As the candle burns, it heats the air inside the bottle. This causes the air to expand, and some of it escapes from under the bottle. Eventually, the candle flame goes out because the oxygen inside the bottle is used up. When the flame goes out, the air inside the bottle cools down. The cooling air inside the bottle creates a lower pressure compared to the outside air pressure. This pressure difference causes the water to be pushed up into the bottle until the pressure inside and outside the bottle equalizes. Pour the vinegar into the glass. After that, put the egg in. As soon as the egg is submerged in vinegar, you'll notice bubbles forming on the surface of the eggshell. These bubbles are carbon dioxide gas produced by the reaction between the acetic acid in the vinegar and the calcium carbonate in the eggshell. Over the next 24-48 hours, the acetic acid continues to react with the calcium carbonate, dissolving the eggshell. Look what happened after 48 hours. The vinegar has completely dissolved the eggshell. The egg is so soft and bouncy, just like a rubber ball. You'll need copper sulfate, calcium chloride, sodium chloride, lithium, and magnesium sulfate. Put a bit of each in a dish and add some ethyl alcohol. Light them up and see what happens. It's pretty amazing. Copper sulfate often produces a green flame. Calcium chloride often produces an orange flame, but this salt is unstable and can be dangerous to burn. Sodium chloride often produces yellow flame, and it's similar to calcium chloride. It's unstable and should not be burned. Lithium metal burns with a distinct red-purple flame. Magnesium sulfate can produce a bright white flame or no distinct color. These experiments can be dangerous to perform, so remember that. Adult supervision is required for this experiment. Use a safe, non-toxic alcohol. Perform this experiment in a well-ventilated area. Be sure to wear protective gear while conducting this experiment. Let's take a balloon and an orange. Cut a small piece of the orange and squeeze the oil from the orange peel onto the balloon. It pops. Why is that? Orange peels have a special oil called limonene. This oil can dissolve rubber. When you squeeze the oil onto a balloon, it starts to eat away at the balloon's surface. Once the oil makes the balloon weak enough, the air inside pushes out and pops it. We need a glass of water and a piece of cardboard. Place the cardboard on top of the glass and turn it upside down. Let's see what happens. Wow, the water doesn't fall out. Even when I remove the cardboard, the water stays in the glass. Why doesn't the water spill out of an upside-down glass? This is actually a simple trick, but let me explain why is that. When you place a card on top of a glass filled with water and turn it upside down, the air pressure outside the glass is greater than the pressure inside the glass. This difference in pressure creates a force that pushes the card up against the glass, preventing the water from spilling out. The water molecules at the surface of the water form a sort of skin due to surface tension. This helps the card to stick to the glass and hold the water in place. Why doesn't the water leak out when we screw the cap on tightly? When the cap is on tight, the air inside the bottle can't escape. This creates a balance between the air pressure inside and outside the bottle. The air pressure inside the bottle prevents water from leaking through the holes. When you unscrew the cap, air can now enter the bottle. With the cap off, the air pressure inside the bottle decreases, allowing water to flow out of the holes due to gravity and the water pressure. Let's make magnetic slime. First, mix the baking soda and water. Then, combine the glue and food coloring. Add the baking soda mixture and stir until it becomes slimy. Finally, add iron filings and mix it all together. After adding the iron filings, knead and pull repeatedly so that the iron filings are evenly mixed into the slime. Continue this process until the slime is a uniform color. Now, let's play this magnetic slime. Isn't it cool how it reacts to a magnet? It's like a little slimy monster, right? You can play with it for hours and then store it in a glass container to keep it soft. If you leave it out, it will dry out and become hard. We have a cup of water. Now let's try lighting the cup on fire and see what happens. It only burns the top part of the cup. Why is that? If you set fire to a plastic cup filled with water, the fire will typically stop at the water line. This is due to water's ability to absorb heat very efficiently. As the fire heats the plastic cup, the heat is transferred to the water, preventing the plastic from reaching its ignition temperature. As a result, the plastic above the water level may melt or burn, but the plastic in contact with the water remains intact. We need a CD case and a piece of plastic from it. Remove everything except for the plastic like this. Draw a square on the cardboard, and then draw two 45-degree angles. Use hot stick glue to attach the two 45-degree paper pieces onto the square you just drew. Next, use the plastic from the CD case to stick according to the angles you drew. Open your phone and search for hologram compilation. Look at it. It's pretty cool, right? When a hairdryer blows a ping pong ball into the air, the ball remains suspended due to the Bernoulli principle. The hairdryer creates a stream of fast-moving air. According to the Bernoulli principle, as the speed of the air increases, the pressure decreases. This creates a low-pressure area around the ball. The ball stays in the low-pressure area of the airstream because the surrounding air has higher pressure. The upward force from the air balances the downward force of gravity. This keeps the ball stable and suspended in the air. You can also try two ping pong balls. They will also float. For this experiment, you'll need a glass bottle, drain cleaner, and a piece of aluminum foil. Make the aluminum foil into a small ball like this. Next, pour the drain cleaner into the bottle. Quickly put the aluminum ball into the bottle. When drain cleaner comes into contact with aluminum, a chemical reaction produces sodium aluminate and hydrogen gas. You'll notice bubbles forming in the bottle. This is hydrogen gas being released. The reaction is exothermic, meaning it releases heat. The bottle is very hot and can explode, so keep it away from open flames. This experiment should be conducted under adult supervision and with proper safety precautions. Drain cleaners are corrosive and can cause severe burns. Hydrogen gas is flammable, so the experiment should be performed in a well-ventilated area away from open flames. Have you ever wondered how quickly you can empty a bottle of water? The pouring speed is very slow, taking more than 13 seconds to empty the bottle. Now, let's try spinning the bottle like this. See, it's faster. It takes over 4 seconds. But the quickest way is to use a straw. Put the straw into the bottle and tie it like this. Let's see how long it takes to empty the bottle. Wow, it only takes over 3 seconds. Why is that? When you pour water out of a bottle, air needs to enter the bottle to replace the volume of water leaving. If air cannot enter the bottle easily, a partial vacuum can form inside, slowing the flow of water. Twirling or spinning the bottle can create a vortex, which allows air to enter from the sides while water exits from the center. This method, often called the vortex method, insert a straw or tube into the bottle. This method is effective because it provides a path for air to enter as water exits, preventing airlock and allowing a faster flow. We need an aluminum can or any container that can be used to melt paraffin wax. This is the paraffin wax. Turn on the stove and add some water to the pot and heat until the wax melts, and add aluminum powder, stirring well. Take it out of the pot. Now we pour this mixture into a petri dish. Let's see what happens. Wow, it's pretty cool, huh? What you are seeing are called Rayleigh-Benard cells. Why it works: the bottom of the wax is heated while the top remains cooler, creating a temperature gradient. The heated wax at the bottom becomes less dense and rises due to buoyancy. As the warm wax rises, it eventually cools at the top and sinks back down. These rising and sinking motions organize into a regular pattern of hexagonal cells called Rayleigh-Benard cells. The aluminum powder suspended in the wax moves with the flow, making the convection cells visible.